All right, our last chapter 3.5 kind of wrap-up problem has us with a surge curve formula with an adjustable power on x that adjusts the shape of the surge curve, and an adjustable multiplier on x in the exponent that adjusts the horizontal scale of everything. And a here is a vertical multiplier. And we want to find a formula for the x value of the local maximum of this and for the inflection points. It turns out this section at the bottom of the page is too small to actually fit in all the algebra, so we're going to turn the page here. And this one is a fair bit of algebra, but at least there's no real guessing. It's kind of just plug and chug. So we'll say f of x equals a times x to the p times e to the minus bx. And to find the local max, we need to find where f prime, we know it's a local max because this is a surge curve. So what is f prime? Well, a here is a constant vertical multiplier, so I can just use that as it is. I don't need to do anything with that. Other than that, I have the product rule here, so I'm going to make a lot of space, and product rule I think of as this prime times that plus this times that prime. So it doesn't hurt to lay it out that way and then even fill it in on the next line. So x to the p prime times e to the minus bx plus x to the p e to the minus bx prime. And we get what? Px to the p minus 1 e to the minus bx plus x to the p, and then what's the derivative of e to the minus bx? Well, derivative of e to the stuff is e to the stuff times the derivative of the stuff, so minus bx prime. So a times px to the p minus 1 e to the minus bx plus x to the p e to the minus bx times negative b. And remember, I have to have that times there, otherwise it looks like I'm subtracting the b. All right, so we want to set this equal to 0 and solve. Yuck. But we've got we've got 2 e to the minus bx's. We can factor that out. Maybe that'll help. So we'll get a times e to the minus bx px to the p minus 1 plus x to the p times negative b. And then we notice we've got x to the p and x to the p minus 1. We can factor one of those out. Even the negative bx. Let's just pull out x to the p minus 1. And then we'll have p left over there. And I need an x here. So when I multiply x by x to the p minus 1, I get x to the p times negative b. And now we're going to set this equal to 0 and solve. This is a this is a product. The only way a product can be 0 is if any of the factors are 0, at least one of the factors. So we can ask, when is a equals 0? Well, it said a was a positive constant, so never. When is e to the minus bx equal to 0? Never. You can't get a 0 by putting in a finite number to e to the power. When is x to the p minus 1 equal to 0? Well, that's true at x equals 0. We said we were only really interested in x strictly greater than 0, but I'm willing to make an exception here. And then the question, when is this last term equal to 0? When is p plus x times minus b equal to 0? So we can solve that and say subtract p from both sides. So you get x times minus b equals minus p. And then divide both sides by minus b, you get x equals minus p over minus b, or just p over b. So our derivative is 0 when x is 0 or when x is equal to p over b. So let's write that down. So f prime equals 0 at x is 0, or x equals p over b. Well, it's a good thing we said b was positive, otherwise we would be possibly dividing by 0. Okay, so that tells us where the local min or max is, and then the next step is to find the inflection point. Take a sec to think, how are we going to find the inflection point? Well, the candidate inflection points happen where f double prime is 0. In this case, we know there's an inflection point to the left and to the right of the max because we know it's a surge curve. So we can just say inflection points where f double prime is 0, which means we need to take f double prime. So let's look back up at f prime. If I did it on this form of x prime, I'd have 3 things in the product rule, which is a pain. But if I go 1 row above, then I only have this and that in the product rule. So let's copy that expression here. We'll just copy it for ease of reference. So a times e to the minus bx times px to the p minus 1 plus x to the p times negative b. So then let's plan out f double prime. That vertical multiplier will stay there. And then we'll have this prime times that plus this times that prime. So it's going to be a lot of algebra, but it's just kind of cranking through. It's not so bad, actually. So e to the minus bx prime times all that stuff, px to the p minus 1 plus x to the p times minus b plus e to the minus bx times, can we just take the derivative of that right now? It's just a power rule stuff. So the p gets copied, the p minus 1 comes down, we get x to the p minus 2 plus px to the p minus 1 times negative b, like that. All right, are we done with the calculus? Nope, there's still a derivative to take there, but it's not so bad. What's the derivative of e to the minus bx? It's e to the minus bx times negative b for the chain rule, times all that stuff plus all that stuff. I'll just say same. All right, and we want to figure out where this is going to be equal to 0. So we want to probably apply that same rule as before. If I can make it a product of things, then I have to know where each of the products, where any of the factors is 0. So again, I have an e to the minus bx, so I'll factor that out. And then I have minus b px to the p minus 1 plus x to the p times minus b plus p minus 1 x to the p minus 2 plus px to the p minus 1 times negative b. And then let's factor out, last time we factored out an x to the p minus 1, let's factor out an x to the p minus 2 because that's our lowest power here. A ex to the negative b, x to the p minus 2. And then what do we have left? We have negative bp x, negative b, so positive b squared, x to the 2. So the x to the 2 times x to the p minus 2 will give us x to the p. And then we've got p minus 1, and then we factored out that x to the p minus 2 plus negative bp x. All right, this would be a really good time to go type this all into Desmos and also use Desmos's f double prime function to make sure we get the same curve before we do anything else fancy, right? So I've already done that, you can trust me. Now we need to say, where is f double prime equal to 0? Well, that could happen if a is 0, but a is not 0. That could happen if e to the negative bx is 0, but that's never 0. That could happen at x to the p minus 2 is 0, which is true at x equals 0. So we'll just keep that in mind. Or it could happen where this whole thing is 0. It looks kind of ugly, but it's just a quadratic. So let's say, hey, this thing is a quadratic. And let's organize it the way we usually organize quadratics when we're going to use the quadratic formula. We'll have an x squared term, and the coefficient on that is b squared. The linear term, x and x, we have two of these negative bp's, so minus 2bp, pb, whatever, x, and then the constant term is p minus 1. And we're asking, where is this equal to 0? Well, that's what the quadratic formula was invented for, right? So zeros are at, we've already got a b in this formula, so I don't want to call it a, b, and c. And we already have an a. We could use like a big old cursive a big old cursive b, and a big old cursive c. That's not a very good c, is it? We'll call that a c. So we have negative b, so negative 2bp plus or minus the square root of that whole thing squared minus 4 times big A, which is b squared, times c, which is p minus 1, all over 2 big A, so 2b squared. So that is where our the x values of our inflection points. And then also x equals 0, which we're kind of ignoring, kind of not. So let's go type this all into Desmos and check that it worked. All right, we've got our surge curve formula here. I chose some parameters, a equals 1. A didn't end up affecting anything. I can just increase it if I want, doesn't really matter. It didn't affect the locations of the horizontal locations of the max or the inflection points, so it doesn't really matter. Maybe we'll set it to something distinctive just in case it ever does matter. I chose p equals 3 just to give it this nice shape. If we choose p equals 2 and bring a back down, we can see it kind of looks like a parabola near the origin here. If I chose p equals 1 and bring a back down, then it looks kind of linear near the origin, like x to the 1, so that kind of makes sense. If we chose p equals 3, then it kind of looks like a cubic near the origin, like x cubed. And then I chose b equals 6 just so it wasn't 1, just so we wouldn't get any numerical coincidences. It's also often good to choose it to be a prime, so they're really unlikely to have any numerical coincidences. All right, then we got that the local max would be at b over p, and so that's what I've typed in here, and sure enough, that looks good. And then we got that the inflection points, we also got that there would be some kind of point at 0. It turns out here it's a saddle point. And then here's all that quadratic formula goodness. And we get these two values, and we plot them with their function values, and those certainly look like they would be inflection points. How can we check them? Well, if we plot f double prime, at least have Desmos do it for us, then where f double prime is 0, that's where the inflection point should be. So I'm getting 0.2536 here, which matches that, at least to round off. And over here I'm getting 0.9464, which matches that, at least to round off. So if I hadn't felt like doing all that algebra and quadratic formula stuff, I could get a high precision estimate of where that inflection point is by saying f double prime equals 0, but then I wouldn't have it in terms of a and b and p. So when I change the sliders here, I would have to go recheck where is this crossing 0. All right, so that's inflection points and the local max for our surge curve.